Good afternoon. It's January 3rd, 2024. And today, another edition of Moment and Motion. The subtitle of which is determined somewhat later after the talk. These kind of talks, they aren't scripted, they aren't prepared so much, although there's a great preparedness about them in terms of studying these fields, the foundations or study of what is... it can be a theory that is a theory, that is the theory in theory. So, and then that with regards to that, there's not really room for much more than one take of things, and it just kind of is a matter of the stream of consciousness, the train of thought. And I'm notoriously long-winded and make very, very long yet complete and well-formed grammatically sentences. The word we're going to get into today is some more about moment and motion. So one thing I've had some time to do recently, a little bit, is to review a few of the discussions that were taken from the reading from Einstein. And so I very much enjoyed reading Einstein's book, and it's called Out of My Later Years, and there's a copy of it here. And in it, he really details what he calls his final theory of relativity. And he really details a lot of his desiderata and requirements of his theory. And a very large amount of it is framed in terms of moment and motion. And I mean, it's all about that velocity and motion. And at the end of the scientific segment in Einstein's book, when he introduces mass equivalency 2, his new derivation, or kind of like root mc squared, with regards to the traveling wave and these sorts of things, they're really speak to a greater interpretation of Einstein's theory, especially for space contraction, after he, puts special relativity on the side and instead of in front, and as for the causality and the leading from the derivations of things, and put general relativity in front, and has defined his spacial, and these kinds of things, that Einstein's work is greatly appreciated. And it really has that the message that it parts with is, especially at the end, about mass energy equivalency and Einstein's second most famous formula, which most people, even in the field, have no idea about, is quite interesting, quite compelling. So I was very happy to review some of the talks from Einstein's, reading from Einstein, and really feel that there's a lot of cohesiveness, a lot of coherence, if you will, vis-a-vis what's decoherence and recoherence, vis-a-vis normalization and denormalization for quantum theory and such, and the causality associated with such notions as the real wave and these sorts of things. That indeed, and for moment and motion, it's one of Einstein's central topics. And that's in very large part because it's central in all such manners of kinetics and dynamics writ large at all. It is the description that anything that is moment might be statics, but moment and motion is dynamics. So another thing that was pretty great, or I enjoyed from reading last time, was Wertheimer's book on productive thinking, and his detailing of the point concept, the space inversion, and what that entails, just the other way of thinking about these things, or an other way, that combine together to make a wider way, a better way, is that then he has a chapter on Einstein. So if I'm wondering about how to think about Einstein, and I've skimmed through this before, is that Wertheimer has, after finding the sum of the angles of a polygon, chapter 5, and he gets into chapter 6 is about Galileo. Well, we've just been discussing Galileo here as well. He has a reading of Galileo. He talks about the law of inertia, the ancient treatises on physics. That's another great thing, was reading Heisenberg as an introduction to Einstein. It was a pretty great thing. And then as we get to, he talks about the old law, what goes up must come down. Studying the acceleration in the various cases, he saw that acceleration decreases consistently with the angle of inclination. So this, for example, just reflects the other most simple machine, the inclined plane or the ramp. And with regards to how on the ramp, that basically it's possible to raise something to a given height according to the advantage gained by using the ramp instead of just lifting it straight up in the air, which is the usual definition of work. So here he talks about Galileo studying acceleration. Here, after reading Einstein, I needed to have a better grasp of differential equations because, as Einstein put it, it's the theory is a differential system. And so that led to quite the reading into a study of differential systems. And with regards to symmetry, submersions, and sheaves, that it's a nice kind of contained definition of a way to approach the field is kind of a tripos of fields, differential analysis and dynamical modeling. It was so related how everything is basically, according to dynamical modeling, is so modeled by a continuous input parameter called time. And then that with regards to Einstein's total field theory, there's the time, and there was reading as of about Einstein's vouched declaration of his belief in a clock hypothesis, that there is the time. So that made me again happy that Einstein agreed with me already about 70 years ago. That then the reading into the differential equations got into quite a study of the integral equations vis-a-vis the differential equations. And then what was really kind of interesting about the identity dimension, and then as to how that relates to otherwise a separate kind of concern called the stop derivative. And that Einstein's bridges and what goes on in the discussion of the kinetic and kinematic is also related to this mathematical notion, which might be able to help provide this bridge through the cube wall, what is called this stop derivative. In regards to acceleration and the higher orders of acceleration, and the decrease of negative acceleration of retardation and the decrease of acceleration, deceleration, about that we kind of need a dialectic of meeting and parting and coming and going vis-a-vis the plain concepts of motion and rest, because it is in effect the dynamics. And so with regards to dynamical modeling and dynamical systems, it's relevant. And the theory should support it as just from the very most basic central fundamental concept of a continuum, that the continuum is the primary element in the theory. Or if you will, the continuum is the primary element in the theory. So, when a body is thrown up, we have not positive but negative acceleration. And this affects exchange and stuff. Structural dynamic symmetry in Galileo. Galileo's views were confirmed and provided the basis for the development of modern physics. Rather ambitious. Rest and certain natural circular movements were fundamentally separated from opposed to the other movements. Now, rest and constant rectilinear movement are seen together as structurally equivalent and separate from opposed to positively and negatively accelerated movements. This is from my perspective, yet more confirmation of my general opinion, which not all need share, but in some sense, some do. And then with regards to the rhetoric, that is, it's scientific, philosophically, as exercise in psychology. So after this chapter on Galileo, and Wertheimer is a pretty great thinker, and it kind of helps frame some of these things about fundamental changes in concepts. The meaning of the concepts about motion were radically changed in their place, role, and function. The interconnections were viewed in an entirely new structure. A new grouping and dividing took place. When I study programming languages and parsing them, there's quite a bit involved in bracketing and grouping, and then comma and separating. So There's comma as a separator and comma as a joiner. There's bracketing and precedence and vis-a-vis structure and hierarchical and all this kind of stuff in terms of syntax of parsing. And what with regards to, it essentially results in a multi-pass parser of a sort. With regards to that, something like the usual notion of the abstract syntax tree as directed by Backus-Naur format or extended Backus-Naur format, or some of these parser expressions. And with regards to LALR or look ahead and the parser, a finite state machine which can so implement producing an abstract syntax tree as from an input in the usual notion of lexical analysis as after in the syntactical after that, vis-a-vis the input and the character stream and so on and so forth. That these notions of grouping and dividing or composition and decomposition are really very, very usual in such structured languages. Dialects of what result natural languages, the parser. And so then with regards to what sometimes you usually consider as like, well, that's a context-free grammar, your parser won't build for it. It's like, well, yeah, because the one you have there goes 300 miles an hour in a straight line, and just don't look down, kind of a thing. Vis-a-vis a pretty simple model of a multi-pass parser for what are called the railroad diagrams or syntax diagrams. For example, parsing natural languages or as languages like SQL, structured query language. The idea being to essentially implement all sorts of syntaxes in a common grammar that make it so that for different sections of syntax, according to comment and with the parenthetical, or as with regards to the what's called here doc or the block sections, that it's possible to arrive at what's a framework for language parsing that's declarative and deliberate and efficient in terms of building this a syntax sequence vis-a-vis a syntax tree, and then that also as you read into the layers of the code and the layers of the code and the layers of code, and it refines this and lifts it in these blocks to what are recognized objects according to grammar, strictly and loosely. It's a reading of it is also the same as the source text, and it preserves all the way down the markers right down into the source. So such is the notion of a usual generic data structure for natural language representation of all sorts. What were the decisive tasks in the development of Einstein's theory of relativity? Well, we consulted Einstein, and he said it was his last word on the matter. It's kind of thoroughly read. You can find a copy of it, I should so hope, at your library through interlibrary loan, or as finding it on the marketplace of books, or maybe even in just a regular digital form. Out of my later years, the scientific parts. Although this is quite a task, I shall try to make them clear to the reader. A number of issues, such as the question of the ether, the relations to the principles of Galilean relativity, will be excluded from the discussion. So the ether hypothesis is the idea that space is absolute, or that in terms of what's called these days what's called frame dragging and lens othering with regards to the Michelson-Morley experiment, has that, according to ether drift hypothesis, it would be possible to determine that the Earth's movement would be kind of detectable vis-a-vis that it's a flat plane. So we call the terrestrial frame, or the laboratory frame, with regards to Earth-born or space-born experiments, lab frame, the Earth terrestrial frame. So Michelson-Morley was this idea that they dug deep beneath Case Western Reserve University in Ohio or Cleveland, and what they did was they set up a font or a pool of liquid mercury like 20 feet across or something like that. And then around that, what they had was kind of this floating beam from side to side, and then what they do is they have some mirrors set up or otherwise with regards to basically peeping across the lake of mercury and determining from that there would be by theory, there would be established a certain diffraction to set up. So what they found was when they let it come to rest, that it was the null result, and so it's basically one of those things that's said to establish that there's no ether theory. So today, that's called, and you can review something like the notion of Dirac positronic C, which here is also like Einstein's white holes, black holes everywhere C. That's also Dirac's positronic C, this unified field C, that lens aethering and frame dragging is what's called how it's possible to determine basically how fast the Earth is moving around the sun and how fast the sun is moving through the galaxy, and otherwise with respect to central moments, that experimentally it's so. And so the vacuum energy and the ether hypothesis is that these days it's called aether, A-E-T-H-E-R, aether theories. Will be excluded from this discussion. The field which Einstein faced in this gigantic process of thought was very large, since it involved most of the fundamental topics of modern physics, difficult issues unfamiliar to those not acquainted with the complexity of modern physics, which we try to keep simple, and kind of is, and it is better when it is, which is nice. Although the following sketch will of necessity be condensed, I hope the reader will gain an insight into the nature of the decisive steps. He says he was able to sit with Einstein alone in his study and hear from him the story of the dramatic developments which culminated in the theory of relativity. During those long discussions, I questioned Einstein in great detail about the concrete events in his thought. He described them to me, not in generalities, but in a discussion of the genesis of each question. So he's got quite a chapter here on Einstein, and it reads for about 20 or 30 pages, it looks like. Talks about on movement, everything, including the meaning and structural role of time, space, measurement, light, etc., was to be understood in terms of traditional physics. And here he talks about the Michelson-Morley result. So maybe we'll take a look at that in a moment. And then his conclusion of this work called Productive Thinking is dynamics and logic of positive or productive thinking, in which he talks about usual notions of what's the brainstorming, the ideation, the creativity in a sense, combined with rational, clear reasoning, and particularly then for formalists, what make formal methods what reduce to refined, even mechanical inference, which can be more than simply the phenomenological inference, with regards to here that we have an object sense that includes infinity, and basically only includes real mathematical infinity, otherwise being quite often phenomenological. So he kind of separates that into alpha and beta, where alpha is clear on the face of it, prima facie, it's obvious, and beta is thinking is involved, and even counterintuitive thinking is involved in terms of that there's an intuitive sense, and which is often enough times just the easiest way, which doesn't arrive at that. Otherwise, it takes like the extra or these kinds of things. So back to Einstein. He talks about Einstein. It's Gymnasium, which is a German word for high school, a light ray. And he considered he imagined himself as if he was riding the light, if he was the light. And he talks about light determines a state of absolute rest. And so here we talk about flux and the light speed rest frame theory. It's kind of like, well, if light speed is supposed to be infinite, well, then just kind of set it out the other way, and they have the frame move away from it in all directions at once. And then light speed, it just kind of rests on out. It's a complementary theory sitting next to special relativity that then helps cancel some things out that is just kind of then let it aside because its special relativity is local. So it's basically only the same statement as its SR is local, is what governs light, the light like. It was just curiosity that the velocity of light could differ depending on the movement of the observer was somehow characterized by doubt. Later developments increased that doubt. So, light speed restaurant. Constant rate light in all directions. Also, light, just as mechanical processes, seem to know nothing of a state of absolute movement or of absolute rest. This was interesting, exciting. Light was to Einstein something very fundamental. At the time of his studies at the gymnasium, the ether was no longer being thought of as something mechanical, but as the mere carrier of electrical phenomena. So this is before field physics in a sense, and it kind of like Higgs's field. So Higgs is a guy, and he's related to standard particle physics, and the Higgs boson is supposedly like, according to our energy experiments, we determined in our Tevatron that we found a Higgs boson, and its mass, well, it was estimated to be a certain given value, but what we found kind of grows and runs up and out of our standard model physics, but it really put the cap on our standard model physics, and also now it's extra or non-standard. So anyways, the Higgs field is just kind of one of these interfaces. It's kind of the surrounds of the effect of this thing. So it's not like the field, because a field in physics is across the entire universe, and it's just got contents in it. But a Higgs field is not a classical field. A field's a potential. A Higgs field it's just kind of like a surface. And so this was inspired, like mentioning the mere carrier of electrical phenomena. You'd usually consider that to be the electrical field or space, but most likely the electrical field is among other sources of electromagnetic radiation. These days is also known as the Dirac positronic sea. It is the ether again, the aether theory. But only as it's kind of a conceit in terms of our continuous space-time, continuous manifold of space-time. And then it talks about how Einstein studied Maxwell's equations, E cross B and such. What would happen? Light could not be different from the situation with regard to mechanical processes, no absolute movement, no absolute rest. So here the light like it's kind of let out as a particular case of free information running apace, flux, the fleeting, as with regards to some of the earlier mention and discussion of free information and theories where gravity's speed is not finite, and that the geodesy is instantly evaluated everywhere, of course, is a usual tenet, well supported by Einstein, that some people don't know. And so that's one thing, when it was said that Einstein sometimes had to defend himself from his own followers, well, it's because they didn't know that he had these other attachments to his theory, which, keep it real, they didn't, so. The famous Michelson experiment confronting physicists with a disconcerting result. If you are running away from a body that is rushing toward you, you will expect it to hit you somewhere later than if you are standing still. If you run toward it, it will hit you earlier. Michelson did just this in experiments of the velocity of light. He compared the time light takes to travel in two pipes if the pipes meet at right angles to each other, and if one lies in the direction of the movement of the Earth while the other is vertical to it. So this is Michelson. And there's Michelson and Morley. The reader may be inclined to assume that with the light rays moving forward and backward, the difference introduced by the movement of the Earth would be canceled. Negative result. The result of the Michelson experiment in no way fitted the fundamental ideas of the physicist. In fact, the result contradicted all their reasonable expectations. As about classical models of the non-superclassical. Einstein. Lorentz, the famous Dutch physicist, had developed a theory. And this is basically normalizing the units of C as that they effectively reflect, according to algebra, the same thing as asymptotic. So that's after the Galilean, which is compute velocity multiplied by time equals distance. Yeah. Galilean invariance is the most familiar fact of classical mechanics. Re-examination of the theoretical situation. Positive steps towards clarification. For what now followed in Einstein's thinking, we can fortunately report paragraphs from his own writing. He says, Über die Spacial and die allgemeine Relativitätstheorie, Braunschweig, 1916. The passages from Einstein quoted in this chapter were translated by Professor Wertheimer. He wrote them in the form of a discussion with the reader. What Einstein here says to the reader is similar to the way his thinking proceeded. Lightning strikes in two distant places. I assert that both bolts strike simultaneously. If now I ask you, dear reader, whether this assertion makes sense, you will answer yes, certainly. But if I urge you to explain to me more clearly the meaning of this assertion, you will find after some deliberation the answering this question is not as simple as it first appears. So this was about 30 years before he wrote Out of My Later Years. So we rely on Out of My Later Years as being Einstein's lucid, final, comprehensive word on these things. Similarly, Einstein continued with the concept of simultaneity. The concept really exists for the physicist only when in a concrete case there is some possibility of deciding whether the concept is or is not applicable. Such a definition of simultaneity is required, therefore, as would provide a method for deciding. As long as this requirement is not fulfilled, I am deluding myself as physicist, to be sure as non-physicist too, if I believe that the assertion of simultaneity has a real meaning. Until you have truly agreed to this, dear reader, do not read any further. See, he doesn't say that it doesn't have a meaning. He says that it must have a pretty comprehensive meaning. So we've kind of established that it does. And that it's teleological, according to the mechanisms of things why that's so, and also ontological, that our science has it as time symmetry has never been falsified, at least. And that also otherwise, that all such usual models is what reflect real quantities are in terms of real valued positive time. But it's the most usual thing. Simultaneity in distant places here gets its meaning by being based on clear simultaneity in an identical place. What I was thinking about for a second was that the complex analysis is said to, it works. And in part because, A, when the real parts come back out, it works. And B, because that certain properties of its context of rotation work, that it's analytic. But it's to be kept in mind that though you have Euler's identity and the Gaussian analysis and all that it can be written just as easily and well as about the polar, and the periodic, and the rotational in terms of an algebra of such objects, that the entire rest of the machinery of the complex analysis is unnecessary with regards to most of the results of complex analysis. It's a simple and thoroughly investigated and simply derived milieu for an algebraic treatment of some quantities. It's just not that real in some senses. Whereas with regards to at the same time, it's very profound, of course, that just like notions of negative numbers are real, and the root of I is real, that then as regards to structures that in terms of the real quantities only derivable from complex analysis have to do with powers and roots as about those and their singularities and multiplicity theory. That as it's just usually applied as a notion of Gauss and Euler and Euler's identity and Gauss's following, that is by no means irreplaceable. The geometric algebras that kind of arise following that are a richer accoutrement of things with even better and nicer geometric character throughout, which abandons some of the things to do with otherwise the Gaussian and infinite series. And they're not missing that. Indeed, you could look to great modern authors like Pazzaglia and the polydimensional geometric algebras, the Clifford algebras. There's a guy named Hestenes. He rewrites classical mechanics with regards to using geometric algebras. And Sobchak, S-O-B-C-Z-Y-K, Sobchak. And that Hestenes and Sobchak and Pazzaglia and Baylis for the electrodynamics have rewritten a lot of the formulas that we're familiar with and Einstein would be familiar with and in geometric algebras. Those being extensions of what are like complex arithmetic don't include most of what is the usual trappings of Gaussian integral. Similarly, so there's no negative time. Similarly, Einstein continued with the concept of simultaneity. The concept really exists for the physicist only when in a concrete case there is some possibility of deciding whether the concept is not applicable. It's required. Until you have truly agreed to this, dear reader, do not read any further. After some deliberation, you may make the following proposal to prove whether the two shafts strike simultaneously. It's rather a funny way to pronounce that word, but sometimes that's how it is. Simultaneity. We see then that our statements about simultaneity involve essentially reference to movement of the observer. With regards to the events, yeah, I suppose. Here we have what's called the Galilean and Doppler for the linear. It's called parallax. It's used for all such manners of range finding according to perspective. And then in the rotational, as was discussed in reading Einstein, there's differences. He goes back and he's back on the train. I'm on the train. And here it's like I'm Einstein, we're on the train. Now it's going light speed in theory. And light is just falling away. It's falling away. And it's like we're not even moving compared to it, but it's falling away in every single direction once. And he's like, well, yeah, I can see that. Each frame of reference, each system of coordinates, therefore has its special time. And it's funny that he makes a word called spacial. So he'll say it's the special time, but then later he'll say it's the spatial time. A statement about a time has real meaning only when the frame of reference is stated, to which the assertion of time refers. This is where the space-contraction can make for the observed rates can vary, but the clock's only slow or meet. And so what would start, for example, as a very slow rate and increase as you approach something, or as a very high rate and decrease as you go away, illustrates for the persistence of vision. So what Wertheimer calls his phi phenomenon in the Gestalt is that it still comes together that, again, Einstein comes around to saying, hey, I really thought it out, and there is the universal clock hypothesis, and how I did it and kept special relativity up in place with the L principle of light speed, and I keep general relativity in its place with that it is the space frame, and that it does implement the Lorentz invariance, Galilean invariance in the limit. is an edifice of a grandiose hedge, the great grandiose hedge, Albert Einstein. This applies also to the measurement of distances in space, with an exclamation point. Every system has its special time and space values. A time or space judgment has sense only if we know the system with reference to which the judgment was made. We must change the old view. The measurements of time intervals and of distances in space are not independent of the conditions of movement of the system in relation to the observer. And here we detail that as space contraction. Before, such notions of symmetry-flex vis-a-vis symmetry breaking, which a singularity can represent like an anti, an opposite, a reversal. But as well, this symmetry-flex is just like it's continuum, boundary, and barrier. So on either side, there's a cross, a crest of some action, which is as of the collision as well, the cascade. So. Then he talks about history about it, and he says, well, we can't have a machine that does perpetual work without any input. There's no free lunch in this in our theory. What goes up must come down, and it does not stay up necessarily, unless it's far enough away that it just floats on its own, which is its own kind of notion of sufficiency. But here, he says they just talk about the fact that that's always the regular principle. The conservation laws and here continuity laws, the invariants establish that. And then that's symmetry-flex, instead of symmetry breaking, for invariant being a symmetry, and symmetry being a conservation law, and conservation law being a continuity law, as that symmetry-flex is the extremes of the regimes and the running constants that run out, and is with regards to then how, as well in the classical, it's simple, it's just exchange. So again, without too many concepts, without too many rules or laws or principles of a theory of some potentials, super classical, and the principle of least action, or the tendencies and propensities of things to oscillate and be recitative and dissipate and be attenuative, really starts to help add things up. And then with regards to the formulaic, and then how that needs to be for the quasi-invariant, which makes for symmetry-flex instead of the invariant. And we got the theory is called quasi-invariant, say, or the pseudo-differential, as with regards to the Dirichlet problem, and how the time ordering happens with the Jordan curve and Jordan measure, that these are real mathematical aspects of continuity. And my three continuity laws about the line continuity, the field continuity, and the signal continuity. And as we were discussing last time about the polydimensional and the pan-dimensional points in space, and how many sides a point has, it's got none, it's just a point, but how many it has in terms of what can cross it and point to it, or at it, or about it, results is well defined. So these are pretty these form a pretty simple approach to mathematics, fundamentally, that is then providing some also deductive results that do start producing numbers, and explain where some of the stuff in physics is on either side, and don't know or can't say, and so each kind of like so hold it up against this one side, so that then we can kind of creep past this middle because we don't know when it'll drop off. And then ditto this other one, the other side, that there is actually a way straight through the middle. Let's see if they come together. In terms of the desired transformation, this means can a relation between the place and time of events and systems which move linearly to each other be so conceived that the velocity of light becomes a constant? Eventually, Einstein reached the answer, yes. There's a quantity that does this. Its information is free. And the optical That's why it's a quantity of substance. The answer consisted of concrete and definite transformation formulas for distances in time and space. Formulas that differed characteristically from the old Galilean transformation formulas. So it talks about how some of the insight and inspiration went into Einstein's special relativity, the theory that we have in physics today that's said to govern the behavior of light. And how it is governed is that it goes at light speed, and how it goes is according to the geodesy, which is governed by general relativity. Questions. It says Einstein is at heart a physicist. Now we know from reading his out of my later years that Einstein's model of a model physicist is kind of heartless. He can't think. He is it's his duty to provide physics that the physics can be relayed from model physicist to model physicist in rote. Einstein's a philosopher at heart. A philosophical physicist. A philosopher in physics. So Wertheimer is kind of then a psychologist, so he says, the question for the psychologist is, were these axioms introduced before the structural requirements? So he talks about the technique of axioms, and of course, if you're familiar kind of with this idea of axiomless natural deduction, the idea is how to arrive at something from otherwise principles which arise, just kind of like least action, least surprise, most gain, or these kinds of things. Although that's not a usual principle, but it just reflects that least action is kind of the same thing. Gradient descent, steepest descent is just natural application of what goes up must come down. Vis-a-vis that the entropic's original definition was as of the growing of a tree, the creation of organization instead. This is the asymptotic freedom, which is one of the great fundamental concepts learned in the 1970s. The atom, the idea is that it's got a nucleus, and the nucleus is held together by the strong nuclear force. And how it actually is and what it is kind of unclear, because it's holding together a bundle of positively charged protons, which according to the theory of charge would repel each other. So somehow it forms, though they're discrete, because of the 1-to-1 ratio of proton charge to electron charge, that it holds together and makes the atomic number, how that can hold together is called this strong nuclear force. And so what they found in the middle is when they started finding some way to to stimulate fission in the nucleus. The Salam and Weinberg came up saying, and they won the Nobel Prize for this, they said, actually, somehow when we started blowing it up, and then it worked that the gluons and quarks the gluons were holding together the quarks of our model of the nucleus itself, that in the middle it's not perfectly like the heart of the diamond or the coal compressed to the diamond. It's free in the middle. It's asymptotic freedom. This is an example where the formula kind of goes up and up and up and then drops to zero. So asymptotic freedom is one of the most telling real things that must be according to some superclassical relation in effect. And it's almost exactly like how Einstein builds up his law of the bridge. And it's which is like, I took a singularity and I added another one and then I left it in, and so you can use it as a bridge, but it has a central moment, but now it's a singularity. There's no singularities in it. It's kind of like, then he's like, am I bad for saying this? That's kind of how Einstein carried it forward, but that's how he helps bring to classical mechanics, classical mathematics, what this sort of superclassical or extra, we just say extra instead of associating it with the superior or something like that, in terms of superior and inferior or super and sub and this kind of stuff. the superclassical, the extra classical, that these are among the ways that Einstein has helped pull these into his theory in terms of algebra and these kinds of things. So Einstein, after Michelson, he's like, great, my L principle holds up just great, and so he was able to carry it forward, and he became very successful. Now, Wertheimer says, in late years, Einstein often told me about the problems on which he was working at the time. There was never a blind step. When he dropped any direction, it was only because he realized that it would introduce ununderstandable arbitrary factors. Sometimes it happened that Einstein was faced with a difficulty that the mathematical tools were not far enough developed to allow real clarification. Nonetheless, he would not lose sight of his problem and would often succeed in finding a way eventually in which the seemingly insuperable difficulties could be surmounted. So that's just some great more reading from Wertheimer there. And then he talks about truth itself, as we talked a little bit about truth itself and our detachment from it, and that though it's there. All right, what are we looking at here? So then I've been reading some more of D'Espagnat. And D'Espagnat, he wrote this book. It's called On Physics and Philosophy. And what it's about is, and we read some of this last time after reading from Wertheimer again, so again, we're just kind of reading from Wertheimer and D'Espagnat, is he's exploring, after Bohm and the idea that there's implicate order and that there's a real continuum, and all these things that have to do just like Einstein has for his model physicist as a model philosopher. D'Espagnat, he's kind of got this warring internalization of the model physicist and the model philosopher, and as well the bookkeeper of all the arguments that go into derivations, is so arrive at why one can say that one can have maintained this thorough course throughout, and that nothing can be not acknowledged. Because everything is part of the didactic and the dialectic. Yet somehow all of it together must arrive at a holistic, comprehensive, thorough consistency. And so where we're at is about 8 pages since last reading about the experiments of quantum mechanics that establish the particle-like and the wave-like nature of particles and waves in particle-wave duality, and that also it's wave-like, which is what this book is kind of reaching toward as it goes further into it, that it's getting interesting with regards to otherwise it just being kind of a conservative extension, which essentially can be a monument to that which is good in our canon, but says nothing of interest because we have canon for that instead. So he's talking about the wave function, the state, and the state vector. So that's like the moment in motion and moment in motion. Moment in motion. Restoring a strong objectivity. So reading ahead a bit, let's see if we can find something interesting or just something that kind of speaks to the mind. That Bohr identified objectivity with intersubjectivity is a fact that the quotation above makes crystal clear. In view of this, one cannot fail to be surprised by the large number of his commentators, including quite competent ones, who merely half agree on this, and only with ambiguous words. It would seem they could not resign themselves to the ominous fact that Bohr was not a realist. Well, you can be a realist if you have this extra augmented object sense and a number sense and a word sense that are only purely mathematical, thus admitted to the phenomenological as the prototype of the real continuum. Be a kind of extra realist. Orthodox quantum mechanics. And a lot that has to go on with the rules of quantum amplitudes, the classical propagation thereof, the interpretation of that, and so on. This is from reading from the Path Integral. or is 4 about the path integral. Above, a sentence from Bohr was quoted that clearly shows that his own notion of objectivity coincided with the one we termed weak. It is true, nevertheless, that before the time when he wrote this, Bohr, Niels Bohr, B-O-H-R, had introduced his famous complementarity notion. So we got unitarity and complementarity and orthogonality, and they're all kind of required and pretty much everywhere. And so when you got into notions of like, well, we're trying to investigate symmetry breaking or set up something and be an experiment which would demonstrate symmetry breaking because then we get prizes in physics, it's framed in terms of these concepts. That some authors thought a kind of revived original realism, whether original means as from the unorigin or as making an origin, might be construed on that basis. The main difficulty at this point is that Bohr himself never gave any explicit definition of what he meant by complementarity. So here's just that there's complementary duals in all things. It's if there's an axiom that starts all things, it's the inverse. That's how we arrive at from this something or nothing, from nothing something. It's inverse. So complementarity is just that there's diversity and variety in a sense that reflects on any otherwise, piece of a thing, the rest of it. So it's definitely with regards to the complement, that which union makes a whole. When in ordinary life we speak of two complementary descriptions of the same object, we mean that these descriptions are partial, but in a way opposed to one another. Well, no, that's not necessarily so. That's not necessarily so. I don't agree with that. That they are as two photographs taken of the same object, one full face and the other one in profile, so that they can be combined, and that quite naturally this yields a more detailed knowledge of the object. Now, as is most well known, this commonplace idea is not the one that Bohr referred to. According to him, it is admittedly true that when no set of classical concepts entirely covers up the thing to be described, still some of them yield the information of a certain kind and may be used, together with the other ones called compatible with them, for building up a representation of the object. But the picture thus obtained is valid only within the realm of well-defined experimental conditions corresponding to the possibility of performing joint measurements of the physical quantities these concepts represent. So he went from being just like a usual person's notion of meaning intuition or being unsurprising or being as via appearances or being known to not be as of appearances to being an entirely otherwise insensate Einstein's model physicist. So D'Espagnat does have along with him a representative with the comportment of an Einstein's model physicist who does not think but follows the philosophy of science exactly and for all purposes. In other words, it is impossible to combine the two pictures in order to form a description more detailed than the ones yielded by each one separately. So speaking out the gestalt here in the fragment and the whole and this kind of thing is that the complementary dual provides all sorts of notions about how that frames a space for inductive impasse both sides, that bridging the inductive impasse is about the most important development that needs to be attached to logic, for mathematics, for continuity theory, to then get canonized, that is reflected in a word and a number and object sense, that would automatically equip so much the rest of it that at the same time it would need to be kind of have heralded an entire litany of why it was usually inapplicable for people that are naive or otherwise don't appreciate its true and real character. For whom the usual unbounded is perfectly suitable for all such ultra-finitist matters as necessary. Yet such is Bohr's complementarity. On the contrary, within the Bohr approach, the forms in question, nay, the objects themselves, depend on the experimental conditions. So this is just the configuration energy experiment with regards to the superclassical waves, because Despaigne is fully aware of Bohmian mechanics and what it entails. He's here just trying to write up until he achieves a mortarboard of what is the way that can be had rationally, conscientiously. That conscientiously has that the logical and physical conscious demands, or the logical conscious demands for the physicist, to make it so that it can be relayed to a model physicist. Otherwise, it's not a science, it's just kind of a study. So it's to be understood that Einstein, for example, and Bohr, for example, and Wertheimer, for example, all would have been aware of de Broglie, de Bohm, in real wave interpretation, and this extra local, the superclassical. There's this great scientist and physicist and mathematician named Fritz London. And so when it comes to things like superconductivity and the behavior of materials at near absolute zero, or as well as some things to do with superfluidity, he wrote a couple of books with mathematics, kind of helping to outline what for Einstein is his bridge and getting into central symmetries as about the classical mathematics thereof. So Fritz London is, and I'll have to dig it up, is having some books that have what would be seminal in terms of being original about the superclassical and the continuum mechanics. Upon reflecting on Bohr's views, we must always keep in mind the essential role they impart to the experimental conditions. To, in Bohr's words, the conditions which define the possible types of predictions regarding the future behavior of the system. For indeed, according to Bohr, these conditions constitute an inherent element of the description of any phenomenon to which the term physical reality can be properly attached. Here, it's one thing to say that, for a particular configuration that you give our grant board $1 billion and we'll spend most of it to make a collider, and the very highest extremes, we'll have one simple formula and we'll be able to add an extra zero. That is, you might imagine that a model of greed would see that as one of the best ways to find a way to proceed, just for their interest and gain. Whereas a model physicist who also has to say, arrive at that if they're wrong, that there's a penalty. They would then need but they still need to fill out all the science. Then you can well imagine they would have a much more sort of principled course first, thinking it over and having it thought out before, buying a golden shovel and a giant pair of scissors. Well, all right. Hey, Tempus Fugit. Roll into Omnes, Griffiths, Gell-mann, and Hartel. Omnes' approach applies, just like Bohr's, standpoints that are definitely at variance with it. So, measurement and quantum superposition effects. Today they've invented what's called the atomic clock. So the atomic clock is basically that even the second is defined in System International as so many transitions, the time of so many transitions of the cesium atom as so indicated by a very particularly accurate matters. And then an atomic clock is basically the idea is, well, how can we implement, it's hard to even implement an accelerometer. There's Like if you want to figure out from a mobile device, and you say one of these things on this system of the chip will be a board next to among all the antennas and the wave meters or whatever you want to call it, and all these medical devices they're onboarding to the phone. It's like, well, what if you just drop it? How would it know what its dead reckoning was? And in fact, could you power it enough so it just kind of slows as it drops until it drops softly with an accelerometer in reverse? Has that the atomic clock lattice basically has that it will detect space contraction. You make an array of these, and so it's basically is a motion detector without anything except the effects of the transit of space-time. They say that general relativity is proved its vital importance by making it so that GPS satellites point right. But what happens is that GPS satellites are kind of launched in the air, and then their dead reckoning is advised by the clocks on board changing. They compare that to what they get from Earth, so they know how space contraction changed the ephemeris around them. So yeah, general relativity is key for that, because otherwise the notions of the clock is then corrected further for the rest of the usual component. Hey, I hope you enjoyed this today. As far as I know, it's entirely accurate, entirely modern, and in terms of science, it's for a theoretical physicist who wants that their model physicist is equipped with the least most and thus is provided phenomenology, and then also an object sense and the objects for mathematics of continuum mechanics that mathematics owes physics. They'll be way ahead of the usual coattailing and wallpapering set. Hey, have a great day. Moment in motion.